Here is a combined summary of the 2 pages. Time-resolved optical shadowgraphy of solid hydrogen jets is presented as a testbed to benchmark particle in cell (PIC) simulations of high-intensity laser-solid interactions. The testbed is designed to experimentally validate PIC simulations, which are crucial for modeling kinetics-dominated plasmas in relativistic and ultrarelativistic laser-solid interactions. The transition from relativistic to subrelativistic laser intensities, where correlated and collisional plasma physics become relevant, is reaching the limits of available modeling capabilities. This calls for theoretical and experimental benchmarks and the establishment of standardized testbeds. The testbed uses a laser-irradiated micron-sized cryogenic hydrogenjet target, and time-resolved optical shadowgraphy of the expanding plasma density is used to determine the bulk-electron temperature evolution after laser irradiation. Hydrodynamics and ray tracing simulations are used to complement the experimental data and determine the bulk-electron temperature. A study of isochoric heating of solid hydrogen induced by laser pulses with a dimensionless vector potential of A0 approximately equals 1 is presented as a showcase. The comparison of the bulk electron temperature of the experiment with systematic scans of PIC simulations demonstrates that the initial surface density gradient of the target is decisive to reach quantitative agreement at 1 ps after the interaction. The testbed is ready for controlled parameter scans at all laser intensities of A01. The technical realization of optimal laser-target interaction conditions and the further development of available simulation tools to correctly capture all occurring physical processes during the transition of the target from an initially solid state to an ultrarelativistic plasma state represent the key aspects. The bulk electron temperature after isochoric heating represents a specifically feasible endpoint to benchmark the entire modeling chain of non-thermal equilibrium that can be computed by PIC simulations, including laser acceleration of electrons and their thermalization to a single temperature within the target bulk. Experimentally, the determination of the achieved bulk electron temperature most often relies on spatially and temporally integrated X-ray spectroscopy. Time-resolved optical shadowgraphy of the induced expansion provides a measure of the bulk electron temperature subsequent to isochoric heating. The testbed platform consists of a laser system, a target system, and an optical diagnostic system. The experiment is conducted with the Draco 150 TW laser at the Helmholtz Zentrum Dresden-Rossendorf. The target is a continuous, self-replenishing jet of cryogenic hydrogen. The optical diagnostic system uses time-resolved optical shadowgraphy to visualize the expanding plasma density. Hydrodynamics and ray tracing simulations are used to determine the bulk electron temperature evolution. A chi-2 fit of the simulated to the measured shadow diameters is used to derive the best matching hydrodynamics simulation and the corresponding electron temperature evolution. Here is a combined summary of pages 3 and 4 of the research paper. The experimental setup involves a 37 Fs pump laser interacting with a cylindrical hydrogenjet target, with time-resolved high-resolution shadowgraphy utilizing a single microscope and 2 simultaneous backlighters. The pump probe delay is variable, with a temporal resolution of 175 Fs. The experimental data is blurred by the pulse duration, and dispersion effects in the beam path cause a fixed delay of 4.6 ps between both probelaser pulses. The measured shadow diameter from two-color optical shadowgraphy is shown in Figure 2a, with a pump probe time delay scan in steps of 5 ps. The shadow diameter increases with pump probe delay until volumetric transparency sets in, which occurs between 20 and 25 ps for the 258 nm probe and between 45 and 50 ps for the 515 nm probe. The difference between the shadow diameters enables the calculation of the corresponding scale length L0, assuming an exponentially decreasing plasma density surface. A hydrodynamic simulation is used to model the density evolution of the hydrogen plasma, driven by a 2-temperature adiabatic expansion. The simulation tool Flash is used to perform 2-temperature hydrodynamics simulations in 2-dimensional radial symmetry with the hydrogen equation of state FPEOS. The initial electron temperature T0 and initial plasma diameter D0 are free parameters, with T0 approximated by 10 electron volts. A ray tracing simulation is used to model the shadow formation of each probe beam, transforming the simulated density profile into a two-dimensional distribution of refractive indices via the dispersion relation. The calculated spatial distribution of refractive indices is inserted into a virtual optical setup, reproducing the experimental imaging setup and beam path. The light distribution in the image plane is calculated, showing the formation of a shadow with sharp edges. The simulated evolution of the shadow diameter is compared to the experimental data, with a Chi2 fit used to find the best matching hydrodynamics simulation. The total Chi2 distribution between the experimental data and all HDRT simulation data is shown in Figure 2b. The HDRT fit to the experimental data is shown in Figure 2a. With the simulated evolution of D258 nms and D515 nms of a hydrodynamics simulation with the initial setting T0 equals 250 electron volts and D0 equals 3.5 micrometers, case alpha, shown as solid lines. The paper presents a novel approach to understanding the high-intensity laser-solid interactions through a combination of hydrodynamic simulation and ray tracing (HDRT) fit, as well as particle-in-cell (PIC) simulation. The authors utilize the HDRT fit to determine the heuristic initial bulk-electron temperature T0, which ranges between 250 and 300 electron volts at 0 ps delay. This temperature range is derived from the experimental data and its comparison with the hydrodynamics simulation results. The HDRT fit is applied to simulate the temporal evolution of the bulk electron temperature, providing a heuristic electron temperature evolution subsequent to isochoric heating and thermalization of the bulk electrons. The simulation utilizes a 2D 3V PIC simulation tool, PI-CON GPU, to model a fully ionized spherical hydrogen column. The target density distribution follows a specific model, with an unperturbed target diameter of D0 equals 4.4 micrometers and a surface scale length L0 equals 0.25 micrometers. The laser is incident along the y direction and polarized in the x direction, featuring a Gaussian shape in space and time, a pulse duration of 37 fsfWhm, and a laser spot size of 14 micrometers fWhm. The simulation box is 32 × 32 square micrometers with absorbing boundary conditions, using a cell length of 0.8 micrometers, 96 and 240 macroparticles per cell. The simulation includes a relativistic binary collision mechanism. The results of the hydrodynamics simulation and ray tracing simulations are presented in Figure 3. The radial electron density profile from the hydrodynamics simulation is shown in Figure 3a, with corresponding shadow diameters D258 nm derived by ray tracing simulations indicated by dashed arrows on the top. The electron and proton temperatures of the target bulk at zero radius versus time are given in Figure 3b. Figure 3c displays the top view of the distribution of refractive indices, N258 nanometers, gray color scale, calculated from the radial electron density profile at 15 ps delay. The distribution is placed in the object plane of the ray tracing simulation, and refraction of the 258 nm probe rays is visualized by the purple lines. Lastly, Figure 3d shows the light distribution in the image plane of the ray tracing simulation, with the shadow diameter D258 nm measured at half of the unperturbed background intensity. In Figure 4, the results of the PIC simulation are presented. The simulated electron density profile for different delays is shown in Figure 4a, with the blue and orange lines illustrating that the electron density at 0.2 ps delay does not significantly differ from the initial state at 0.1 ps. The spatial distribution of the electron temperature T at 1 ps delay is depicted in Figure 4b. The temporal evolution of the equivalent temperatures Tn, equation 6, is shown in Figure 4c, demonstrating that thermalization is reached at about 1.5 ps. A comparison between the PIC simulation and the HDRT fit to the experiment is provided in Figure 4d. The research discusses the expansion of hot electrons into the surrounding vacuum, occurring at densities below 0.1 N 800 nanometers. It compares the electron density profiles at different delays, identifying two characteristics: adiabatic expansion driven by the electron temperature inside the target bulk and a transiently occurring step in the density profile caused by the thermal pressure of the coronal plasma. The study highlights the importance of thermalization, where all electrons achieve a Maxwellian temperature distribution via collisions. The testbed utilizes a pure hydrogen target, allowing for comparison with analytical calculations without further approximations. The discussion focuses on the dependence of heating on the surface density scale length of the target, demonstrating a variation in bulk electron temperature with initial scale lengths between 0 and 500 nanometers. The results suggest a change in laser absorption mechanism from vacuum heating at small scale lengths to resonance absorption at higher ones, affecting the bulk electron temperature. The study also investigates the influence of different parameters on PIC simulations, including the assumption of an initially fully ionized target, radiative cooling, and the difference between 2D 3V PIC and 3D PIC simulations. The research paper introduces a testbed designed to experimentally benchmark particle and cell (PIC) simulations of laser-irradiated micron-sized cryogenic hydrogen jet targets. Time-resolved optical shadowgraphy using two spectrally separated laser beams measures the temporal evolution of the plasma density. A fitting approach by hydrodynamics and ray tracing simulations enables the determination of the bulk electron temperature evolution after the laser energy was absorbed by the target. HDRT fit. A showcase of the testbed studies isochoric heating of solid hydrogen by laser pulses of 37 fs duration in a dimensionless vector potential A0 approximately equals 1. The HDRT fit yields a bulk electron temperature between 250 and 300 electron volts after absorption of the laser energy, supported by systematic scans of PIC simulations. The results confirm that, due to the interplay of vacuum heating and resonance heating of electrons, an exact determination of the surface density gradient of the target is key to achieve quantitative agreement of experiments of high-intensity laser-solid interactions with PIC simulations in the regime of A0 approximately equals 1. The showcase demonstrates the readiness of the testbed for controlled parameter scans at all laser intensities of A01, which is particularly relevant as PIC simulation tools develop towards the inclusion of physics models at subrelativistic laser intensity levels. By extending the platform with additional multicolor probes and including diverse atomic target species in the future, the platform establishes a path towards a sophisticated, versatile testbed to systematically explore plasma opacity as well as ionization and recombination dynamics in laser-heated plasmas. Here is a combined summary of pages 11 and 12 of the research paper. To investigate the plasma expansion process, the authors calculate the Knudsen number Kane, which indicates that hydrodynamic simulations are feasible for this process. The thermal velocity of electrons, mean free path length, and Debye length are calculated, showing that the plasma is weakly coupled and weakly magnetized. The authors utilize the simulation tool Flash, which is commonly used for high-energy density physics. However, uncertainties arise from the hydrogen equation of state and the assumption of two-dimensional radial symmetry. To address these uncertainties, the authors test three different hydrogen equations of state, EOS, FPEOS, FEOS, and Flash EOS and compare them to the benchmark Sesame EOS. The results show that FPEOS fits Sesame EOS best, and the plasma density evolution using FPEOS is consistent with Sesame EOS. In the PIC simulations, a fully ionized plasma column is assumed, which is justified by the critical field of barrier suppression ionization of hydrogen. The authors estimate the energy loss by radiative cooling using analytic calculations and the non-local thermal equilibrium tool FLYCHK. The results show that Bremsstrahlung radiation is the main mechanism of radiation loss, and the radiation loss per electron is negligible compared to the relevant electron temperatures. The authors compare the isotherms of the different EOS and show that FPEOS fits Sesame EOS best. They also compare the electron density profile using Sesame EOS and FPEOS, which confirms the consistency of both EOS. The energy loss by radiative cooling is calculated using the results of the PIC simulation, and the total radiation loss is given by the sum of bound-bound, free-bound, and free-free radiation. The authors find that the total emitted power is approximately equivalent to the power of Bremsstrahlung radiation. In the context of high-intensity laser plasma interactions, the primary mechanism of radiation loss is Bremsstrahlung, or free radiation. This is evident from the results of the PI-Con GPU simulation, which demonstrates that the radiation loss per electron is lower than 0.1% of the relevant thermal electron energies. Consequently, radiative cooling can be neglected in this scenario. To further explore the differences between 2D 3V-PIC and 3D PIC simulations, a comparison is made using a hydrogen target with a diameter of 1 micrometer. The 2D 3V simulation utilizes a box size of 32 × 32 square micrometers, x, y, and the 3D simulation uses a box size of 8 × 8 × 12 cubic micrometers, x, y, z. The total length of the hydrogen target is 4 micrometers into the z direction. The cell size is 0.8 micrometers, 96, and the number of macroparticles per cell is 240 for both simulations. The 3D simulation is stopped at approximately 400 fs. The electron temperature evolution from the PI-Con GPU simulation is compared with the temperature evolution calculated by taking into account the low-temperature collision correction. The collision frequency of the PIC simulations does not include electron-phonon scattering, which is significant at electron temperatures below the Fermi energy. By assuming a uniform distribution of hot electrons in the plasma column and in the laser spot, the hot electron density is calculated as 1.29 × 10 to the power of 22 cm³. The current density of hot electrons is then derived as 2.48 × 10 to the power of 17 A per square meter. From the equations provided, resistive return current heating is dominant for the heating of bulk electrons. Consequently, the equation for the temperature evolution is simplified to include only resistive heating. The electron conductivity is given by the formula sigma T equals N squared, mi nu A, where nu A is the electronian collision frequency, calculated using Spitzer's formula. The electron temperature evolution from the PI-Con GPU simulation and the calculated temperature evolution, taking into account the low-temperature collision correction, are compared. The results indicate that the low-temperature collision correction has a minor impact on the temperature evolution, as shown in Figure 9, c. The current density of hot electrons calculated from the PI-Con GPU simulation is depicted in Figure 9, b. Here is the combined summary of pages 15 and 16 of the research paper. The paper addresses the electronian collision frequency in a hydrogen plasma, which is crucial for understanding the energy transfer from hot electrons to bulk electrons. The collision frequency is corrected for low-temperature collisions, where Spitzer's formula is invalid due to the plasma's degenerate state. The corrected collision frequency, nu EIC, is derived by combining the electronian collision frequency, nu ein, with the collision frequency due to phonon scattering, nu EP. The overall collision frequency is shown in Figure 9a, exhibiting a reversed trend below the Fermi temperature. The return current density, JH, is formulated using equations H9 and H17, which is then used to calculate the influence of the low-temperature collision correction on the bulk electron temperature. The results are compared to PIC simulations in Figure 9, b, and c, showing minor differences before the laser peak arrives on target, but identical results afterwards. The effect of the Coulomb logarithm on the bulk electron temperature is investigated using PIC simulations with varying Coulomb logarithm values. The results, shown in Figure 10, indicate a 20% variation in the bulk electron temperature when the Coulomb logarithm changes from 3.5 to 15. The paper also explores the lateral heat transfer, specifically the hot electron pressure gradient in the transverse direction. 3D PI-Con GPU simulations are conducted to investigate the effect of the density gradient of hot electrons on the bulk electron temperature distribution within the laser spot region. The results, shown in Figure 11, exhibit temperature gradients in all directions, with a decrease from 1.7 keV in the laser spot region to 1 keV above and below the laser spot. The temperature distribution in the XY plane is homogeneous within 20%, consistent with the 2D 3V PIC simulation. The local bulk electron temperature is calculated as a function of the local laser intensity, and the results are compared to the 3D PIC simulation. The hot electron temperature, TH(R), is proportional to the laser intensity, I(R), and the bulk electron temperature, T(R), is proportional to I(R), 0.4, as derived in equations J9 and J11, respectively. This research focuses on the interaction of intense laser pulses with matter, specifically the generation of high-energy particles and their potential applications. The authors investigate the temperature variation along the z-axis of a 3D PI-con GPU simulation, showing that the pressure gradient of hot electrons is relevant only outside the focal spot FWHM. They also examine the influence of lateral heat diffusion on the hydrodynamic expansion of the plasma, concluding that it can be neglected in their scenario. The authors conduct three-dimensional hydrodynamics simulations to verify the assumption of two-dimensional radial symmetry of the hydrodynamics simulations. The results show high agreement with the two-dimensional radial symmetric simulation, justifying the utilization of two-dimensional simulations. The paper also reviews various aspects of laser-driven particle acceleration, including the current status and prospects of fast ignition in fusion targets, laser-driven ion sources, and the interaction of relativistically intense laser pulses with long-scale near-critical plasmas. Furthermore, the authors discuss the potential applications of laser-driven particle acceleration, such as in radiobiology experiments, cancer treatment, and nuclear applications. They also review recent advancements in laser technology, including the development of high repetition rate petawatt laser facilities and novel enabling technologies. The paper concludes by highlighting the importance of understanding the underlying physics of laser-driven particle acceleration and its potential applications, as well as the need for further research and development in this field. This research paper presents a comprehensive review of the current state of knowledge in the field of ultra-intense laser-matter interactions, particularly in the context of high-energy density physics and inertial confinement fusion. The authors provide an extensive bibliography of relevant references, covering topics such as laser-driven particle acceleration, relativistic laser-plasma interactions, and the generation of high-energy density states in matter. The paper begins by discussing the fundamental physics underlying laser-matter interactions, including the concept of relativistic transparency, the role of the plasma frequency, and the importance of collisional absorption. The authors then delve into the specifics of laser-driven particle acceleration, highlighting the challenges and opportunities in this field, including the quest for higher intensities, shorter pulse durations, and more efficient energy conversion. The review also covers the topic of relativistic laser-plasma interactions, including the generation of high-energy density states in matter, the creation of warm dense matter, and the production of high-energy radiation. The authors discuss the various experimental techniques employed to study these phenomena, such as proton radiography, Thomson scattering, and X-ray spectroscopy. In addition, the paper touches on the importance of simulation and modeling in understanding laser-matter interactions, highlighting the role of particle in cell codes, hydrodynamic simulations, and radiation transport models. The authors also provide an overview of the various applications of high-energy density physics, including inertial confinement fusion, radiation therapy, and materials science. Throughout the review, the authors emphasize the interdisciplinary nature of high-energy density physics, drawing on concepts from plasma physics, condensed matter physics, and materials science. The paper concludes by highlighting the exciting opportunities and challenges that lie ahead in this field, including the development of more powerful laser facilities, the creation of new materials and states of matter, and the potential for breakthroughs in energy production and medicine.